Hey everybody, my name is Taylor Sparks. I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation, IMMI. I'm here to talk about this article, A Robust Data-Driven Approach for Mechanical Serial Sectioning. This comes to us from the authors Oakley, Chow, Danielson, and Polonsky at the University of New Mexico and Sandia National Laboratory. Now, if you've never heard of mechanical serial sectioning, let me tell you, it's pretty awesome. Once upon a time, back in 2015 or something, I worked on a family of materials where we had a functionally graded carbide. In other words, from the surface going inward, we expected the properties to change. In fact, we actually showed the hardness change, right? And then we tried to relate that to aspects of the crystal structure as we went inward. But that's tricky because you have to either do this by hand, and polishing, it's hard to know how much you're removing at a time. So this is complicated. Now, fortunately, there are people out there like the company UES that produces RoboMet. This is an automated metallography system. And this is the exact tool that they're going to focus on in this paper. The authors point out that, by repeatedly removing thin sections of material and imaging the exposed surface, you can actually create these 3D representations of the internal structure, which is great for lots of things. But they also point out that achieving consistent and accurate material removal is not easy. And that's in some part because of system variability. And so it takes an experienced operator to sort of manually adjust the parameters on the fly, which leads to prolonged collection times, wasted material, just not ideal circumstances. Therefore, in this paper, what they propose to do is to create a model predictive control framework tailored to a run-to-run controller, which is basically going to automate the parameter selection process, improving the consistency of their material removal through iterative feedback and disturbance rejection and accurate tracking. So this work builds on a couple key papers that they point out. The first paper it builds on is this one by Ivanov and Madison, where they introduce the concept of a closed-loop feedback mechanism for closed-loop controls. And then an actual closed-loop framework was demonstrated by Damien Gallegos-Patterson and co-workers. Now, what they're doing specifically in this paper that builds on that previous work is that they're putting together a one-step predictive run-to-run controller, and they think that that's well suited here because it can have both feed-forward and feedback control to eliminate persistent disturbances in this repetitive process. And they point out that, to address the lack of operators' knowledge in system dynamics, the controller also leverages historical data from thousands of hours of data collection to identify a robust differential inclusion model. So when you get into the actual results of the paper, the way that they were able to do this was by first testing it on simulation data. So for example, here they were asking it for 50 slices to remove, I think it's 8 microns at a time. And then they wanted to bump it up and remove 15 microns at a time. And then they were able to show you what the actual removal looked like with their feedback system in place. And once they'd validated this on simulated data, they could actually test this out experimentally to see if it was actually delivering the results that they expected it to. One of the things I liked about this paper is that they actually integrated with the system with a custom open source Python package and a programmable logic computer. They were able to actually control the RoboMet 3D in real time to get that feedback. And they show that it actually matches really well their target removal with the actual removal. Furthermore, they found that the system was able to automatically adjust to recipe inputs for different parameters. Furthermore, they were able to show that the system was able to automatically adjust the inputs in the recipe in order to account for differing materials and the changing materials properties that it encountered. And something they point out here is that obviously this works great for RoboMet 3D, but this could extend to other systems that would normally require expert operator intervention, not just in serial sectioning. And then finally, ultimately the result is just much better sectioning. They were able to show that on average about 40% of the data that would have been normally was thrown out is actually able to be saved here because they were able to do this much more efficiently without losses. So I hope you check it out and learn more about this in the latest issue of IMMI.